So back in 2008, 2009 timeframe, we were occupied, we were leasing facilities both on the Silicon Valley and various facilities, as well as on the East Coast in the Virginia area. So we were anticipating user growth, and in preparation of that, we set a goal to meet that demand. So we want to design and build the most efficient data center ecosystem possible, right? So how we did this is we looked at streamlining our application. We want to reduce the burden on the CPU, develop the platform at which that application would run, minimizing materials, right? And of course, kind of wrapping all of this around with a data center specific to the cooling needs. So in the design of our Prineville data center, we kind of used, there's been a few words thrown around today that all kind of are harmonious with what our objectives were, to be efficient, looking at traditional approaches and challenging them to explore ideas that would allow us to deliver power more economically, use materials more economically, and also lessen the burden on operational staff, making the servers easy and simple enough to kind of maintain. The other element is, evolution and exploration. So we're exploring ideas and new precepts, trying to change the way you might normally traditionally do something. And the evolution of that, from our first project to our latest project, we're constantly iterating, and growth is all about iteration. Learning lessons, not just from our experience, but from the industry such as yourselves. So we all have pretty bright people working for our company, but we don't, of course, have everyone. And by making it part of the Open Compute Forum, it allows us to learn from each other. So we started with our Prineville site. That was our first site. We then iterated and moved on to Forest City in North Carolina. And then subsequently, we've completed our project in Louisville, Sweden. Sorry, it's still going on, right? So part of our site selection, we have a team at Facebook that looks at sources, various locations with the whole criteria of elements for determining whether or not a site is feasible, such as utilities, making sure that we have enough infrastructure in place, and that fiber has the ability to come in to the site with protected routes. So when we chose our site, we had a few goals. We looked at finding the most regular shaped parcel of land possible, with the idea here that we would be deploying not just one building, but potentially a campus environment. When we spend money bringing services to the site, we want to be able to kind of leverage all that capital investment that we've put into the location. We want a site that's large enough so that we can locate not just our current needs, but making sure that we also have some availability for buildings that we don't yet know, or services that we might not yet know what's on our horizon. Equally, what we've done in the design of our data center was to use 100% outside air. That was one of the objectives of our desire. And so what was important for us is to know the prevailing wind direction, because we wanted to be able to capture the wind like you would in a boat sail. And we would construct our projects from upwind and down so that we're not, during construction, throwing dust into the intakes of our operating data centers. The other reason why that's important is when we do test the generators, or we need to go on generator due to a utility interruption, that we minimize the chances of recirculating any of that exhaust heat and exhaust flue into the data centers themselves. We want to site the substation so that it is kind of like central for distribution, minimizing the amount of copper that's required, certain economies there, and as I mentioned, the future proofing, right? So this is Prineville. You know, we started with our first project. Our first project was actually only going to be about half of that building. Here you see a master plan for all 3 buildings, and on the idea of future-proofing exploration. Of the 3 sections that you see on the far right-hand side, we actually are deploying what you may have heard already, our cold storage solution for handling our photo storage that is randomly accessed. The other element that's associated with this design is using, being light on the site. We've done, the footprint of the building was to kind of minimize the amount of disruption to the soil, to the siting area, replanting some existing vegetation, natural vegetation, and reusing some of the excavation rock. We wanted to minimize the amount of truck traffic that a project normally might generate. Using materials that are readily available locally with the precast concrete panels, using corrugated metal and insulated glass panels. The idea here is that we're using materials that are rugged, durable, that have a certain harmony with the surrounding of the site. The other thing we've done with this project is also introduce a rainwater collection. Facebook's constantly exploring alternate energy sources. For Prineville, we did install a 99 kilowatt solar array. This facility here provides power to our office needs, and we're continually looking for opportunities for using the direct current in the data center, exploring other options for providing power to our servers, minimizing the amount of conversion. In Forest City, this project here was interesting. So North Carolina is ripe with incredible electrical infrastructure. There were a lot of textile mills and a lot of manufacturing in the area. So Duke Energy has this incredible robust power distribution system that allowed a project such as this one to exist and come up to speed in 10 months' time. So Prineville, our first project was about 14 months. This one, the construction manager in North Carolina, very competitive with the construction manager in Prineville, and we delivered this one in 10 months' time. The idea here also was there was an existing project, existing building where buildings 2 and 3 are, which used to be a boat manufacturer and former textile mill, that we had to demolish and beautify the site. There was an existing stream that was previously run through a culvert, which we daylighted, with the idea again to do great things to the sites that we occupy. The other thing that was unique about North Carolina, so Prineville was great temperatures, nice dry climate, so we could use 100% outside air and just use an evaporative cooling system to provide its cooling. Surprisingly, it also works in North Carolina. Normally you would think, you customarily would associate North Carolina with a higher degree of humidity. And what we found is that we were still able to operate at 100% outside air on evaporative mode because of the relative humidity would peak towards the early morning when it was cooler. And then as the day would warm up, the RH would drop, so it would be within our psychrometric envelope. But our bin data said we didn't need any other mechanical cooling, but the ASHRAE 50-year indicated that there would be about 50 hours a year in which we might have to run some type of trimming. And we installed DX cooling coils to peak shave any potential excursions in humidity. To date, we have not had to operate that system. Luleå, Sweden. It's a more constrained site, incredible weather conditions, a lot of free cooling. I think its warmest day is 86 degrees, right? So this site here, we want it to be located in Luleå for various reasons. Incredible, again, electrical distribution scheme, electrical distribution infrastructure. And it's also located on a technology campus. So a lot of positives for locating here in Luleå. One of the lessons that we learned from Luleå that we've kind of integrated into our other subsequent projects was some of the building materials. Both Prineville and Forest City used precast concrete panels. In Forest City, we introduced insulated precast panels. In Luleå, the material of choice is insulated metal panels. So we've kind of adopted that in our subsequent projects. So much so that we are now using it as interior partitions within the actual data center penthouse spaces. It goes up very quickly, again, reducing the amount of material that one would generate in the construction of one of our centers. There's a summer day in Luleå. I'm kidding. Right, so stepping back a little bit, some of our bases of design, how we designed our facility. Like any data center, we wanted to have the data halls to be as regular and optimized as possible. And we've thrown the word around today of elasticity, and I'll tell you a little bit about that. So when we first designed our Prineville facility, we had anticipated that we would deploy 56 feet long hot aisle containment panels so that we could handle our server load at 6.5 kilowatts. Well, as we were developing, the project design has a different cadence than, say, the server design and the application design. Well, as we get closer, we realized, the server loads weren't as hot as we were early anticipating, so we had to scramble a little bit and make sure then we had enough white room to accommodate additional servers to make sure that we're not going to strand any power in the data hall, which we then iterated in Forest City, then again in Luleå. So in Forest City, we've made the data halls larger and added more white space. So it started with this triplet right here. Here what you see in the middle is our DC UPS and our two open rack triplets that would flank the DC UPS. Now, the DC UPS does not require as much air movement as your server rack would. And so it kind of lends itself as an optimal location for locating our columns. And because we wanted a clear data hall space with limited obstructions, no columns in the way of our overhead distribution, we located our columns in the hot aisle containment section of our data hall. Because what we were developing is that all our technicians would only have to service the server from the cold aisle, right? So power and data would drop on that cold aisle side. So it established this 14-foot module. So then we developed this structural grid that's 28 by 32 feet. We used a 16-foot pitch for our hot aisle containment. And this allows us to locate any diagonal bracing, any other structure associated with supporting the facility within these hot aisles, because limited service would be needed in those hot aisles. Compartmentalization. We designed the facility, of course, so that it would be compartmentalized in the event of something, say a fault were to occur or some smoke or something. We contain that fault to the one data hall, but also then allowed us the ability to turn up the facility earlier. By having this compartmentalized solution, we were able to turn up the first data hall 3 months ahead of data hall B, and so while construction is continuing in Suite B, we are actually deploying our servers and getting our network up and running. We separate the electrical rooms. We have 2 water sources. We have the pre-action room on the far right and the reverse osmosis and pump room on the far left. Of the past data centers that I've designed, rarely have we ever introduced any glazing. But by developing this rather rectilinear, pure form, we defined a administration bar. And in that bar, that's where our technicians and full-time staff would reside. So we introduced plenty of daylighting. We created courtyards where our staff could also spend part of their day without necessarily going outside the security envelope of the building. So the public would engage the building from both ends of that bar. And what you see here is an image of our office space with glazing that goes up to about 14 feet. We installed LED lighting that runs on power over Ethernet. Each of those light fixtures actually has an occupancy sensor as well as a daylight sensor. So we do daylight harvesting. And in fact, in the data halls, it's a lights down facility up until you walk through it. So are you guys familiar with Get Smart? You know, when he's walking down the corridor and the lights are turning on, we have that ability with this lighting system. And then to the right is our interior courtyard. So that's the image there. And in that interior courtyard is where we located our rainwater collection tank. And so we use that rainwater collection for flushing toilets as well as taking care of landscape irrigation. We have a multi-purpose room that's on the other end of this interior courtyard. That multi-purpose room is for both for lunch as well as for all hands and for video conferencing. Our MEP support, our electrical bar, our generator yard, and as I mentioned, our reverse osmosis room and our sprinkler riser room. You know, we flank the building with our electrical equipment so as to minimize the amount of copper distance that we need to reach out into the data hall. So again, always with the idea of reducing the amount of material that's necessary. So here's a shot of our electrical room in Suite B. All you see is an MSB. And we use overhead bus duct for tying back into our load banks and our generators. The room is actually pretty empty. One of the nice things about delivering at 480 out to the floor negates the necessity for installing a UPS system. We cool the space as well from the data hall, so that heat from the electrical room then returns back into the same plenum space that we draw the heat out of the data hall, then up to the penthouse. Our generator yard, rather simple. We installed the generators on belly tanks, minimizes the amount of piping that's required. You don't have to worry about a manifolded system. The generator draws whatever fuel it requires from its own tank. We do an N+1 kind of topology. We have a makeup water tank for our reverse osmosis and drawing well water to take care of all our evaporative needs. This is our first reverse osmosis room. And you know, we did a lot of BIM modeling on the design, and we could make it fit. And one of our lessons learned was we made it a little bit too efficient. The installing contractors definitely had their hands full and some gymnastics in deploying the equipment. Subsequently, we've doubled the size of the RO room. So just because it fit in BIM doesn't necessarily meant that operationally was the best solution. So our mechanical distribution, so our premise was that we would use 100% outside air. So looking at our psychrometric chart, what the small polygon here really represents what ASHRAE's guidelines are for cooling a data center. By being in control of the application, the servers, and the facility, we recognize, we have the opportunity to really broaden the ability of using free cooling. So this is the range in which we are delivering our cool air to our data hall. Our servers are able to tolerate higher humidity and a higher temperature. So using a psychrometric chart, we identified the regions in which we would be able to support our services. And so this line here was the magic line for us in Forest City, defining that, okay, ASHRAE 50 would indicate that we would have to do some mechanical cooling to peak shave so that our evaporative system would work. So depending on the time of year, we'd either be heating the air, returning a lot of the waste heat, and evaporating to bring it up into this quadrant. But one of the things that we were doing in Forest City to contend with situations where we were high RH was just returning more of the waste heat and bringing the temperature up so that we kind of fall naturally into that blue zone. So a typical data center, we've got our cooling towers, we've got our chillers, and our prerequisite air handlers. So what we've done is essentially eliminated two high energy usage components, just relying strictly on outside air. And again, as I mentioned, taking return air to either warm up the air when it's too cold outside. You see the gold section here. When we designed our penthouse, we did a galley, which we would be able to add condensing coils or chilled water coils in the event that we do need to go full recirc in the future. So in Forest City, being concerned and playing conservative regarding the higher humidity potential, we did add DX coils, and that's the section that we located it. So up on the penthouse, it's a custom air handler, right, using evaporative system. We located the supply air shafts that would feed the data hall right down the center of the building and only built as much of the penthouse as we required. So in Prineville, what we evolved into Forest City was adding an exhaust plenum space to contend with any foul weather that we might receive on the East Coast. Here's kind of a diagram of how the air flows through our penthouse. So we take the air from the outside louvers, comes in through the mixing section where we have the dampers to control how much outside air comes in. We then go through our filter section. We're showing here the evaporative coils, the condensing coils. Then we have our evaporative system through a mist eliminator to remove any carryover spray that might come along. We used fan array systems to pressurize the supply air plenum, pushing the air down into the data hall, treating the data hall as a large plenum space. So we just pressurize that space. The air would then go through the servers into the hot aisle containment, up into the plenum. Depending on the time of year and the conditions outside, we'd either purge that waste heat or we recirculate it back into the building and doing our mixing. So here's kind of a photo walkthrough of that system. We installed storm-proof louvers. The idea here is to remove any precipitation from the airstream as early as possible, but we still kind of created a wet zone. So we treated the intake plenum as roof. So here we do have floor drains here to take care of any carryover that might make its way through the louvers. And you see on the right, those are the intake dampers drawing the air in, which are up on the left-hand side right now. We have our filter corridor, our mixing area. The bottom louvers are our return heat from our data center. We come through the filter wall, and this is the zone, this is the galley area that is reserved for the introduction of condensing coils or condenser water loop. Moving along, this is the DX coils that we installed in Forest City with bypass dampers. So when we're not using so in the event we don't need to use the DX system, we're just bypassing all the air to minimize the amount of pressure loss. Where we installed a misting system, we have our high pressure pump skids with multiple valves that control how much misting is occurring. And this is all based on outside temperature conditions and humidity. And we then would use the mist eliminator to remove any carryover spray. Our fan arrays, here we pressurize the supply air plenum corridor. The air comes down the data hall. The image on the left is kind of a fisheye lens view, but we've got the overhead supply opening from the penthouse, and we're looking down one of the cold aisles of our data hall. We do all our distribution overhead. So all our cabling IT, our power distribution overhead, no raised floor. Polished concrete floors, just minimize the amount of material, high durable construction. So the air goes through the triplets and the servers, the DCPS, into our hot aisle containment section. So what we've done based on the lessons from our first deployment of Prineville 1A was making sure that we had enough row length in our hot aisle containment so that if, depending on the changing needs of our server SKUs, we have the ability to accommodate more cabinets. We're inside a hot aisle containment section, and the air is coming in, and we just exhaust that up into the ceiling plenum. That hot air then is directed into an exhaust section here with exhaust fans that blow the exhaust heat out. One of the things that we mentioned earlier was the exhaust plenum that we incorporated in Forest City as well as in Luleå. The idea there is that if any precipitation were to kind of backflow through that section, we have a contained space. All our openings down into the data hall are curbed to control any water that might make its way onto the floor. One of the other lessons learned is we've implemented this perforated overhead target plate. The idea here was to improve the air to distribute down the cold aisles. What we were finding is that there was too much velocity coming down. By allowing this, help direct more of the airflow down the cold aisles. Our electrical distribution. So, in a traditional data center, you'll take your 480, 277, go through a dual conversion mode, and then ultimately feed 208 to our servers. So what we've done is eliminated the necessity of that traditional UPS system, designing our servers with power supplies that can take the 277 volt, coupled with 12 volt input from our DC UPS that are located out on the floor. By taking control of the server design and the power supplies, we were able then to utilize power supplies that are very efficient. So, on a typical electrical distribution scheme, you might have 21% to 27% losses. In our design, we're at 7.5, so about 13% delta. So this is our DC UPS. We trickle charge our DC UPS from the 277 volt. The power supply on the server has two inputs, one for 277 and the other one for 12 volt DC. In the event we lose power on the electrical distribution scheme at 277, it automatically flips over to 12 volt to sustain the server operation while the generator is spinning up. And we have installed these RPPs, not remote power panels, but rather reactor power panels. And the idea here at 480 volt 277, we needed something to contend with the leading power factor, and also allows us the ability to kind of control some of the harmonic dissonance. This is also the location where we are able to backfeed anything that might require service. So we have cam lock connections on these RPPs so that we are able to backfeed and service the equipment. We do all our distribution with overhead bus duct and busway, with power panel, with plug-in tap boxes that allow us to adjust per the server requirements. To date, our PUE in Prineville has been 1.088. It's fairly impressive. Better than we had originally targeted. And we publish all our PUE results and as well as our water utilization efficiency as well. Right now, we're about 13% on our water utilization. Other developments. So we're constantly evolving, exploring new ideas. So in Sweden, they had a phenomenal electrical distribution system, very robust national grid, a local grid, a lot of hydropower. And so we asked ourselves, do we need to use generators? So instead, we actually installed 2 substations, and we were able to backfeed into each of the facilities with 2 distinct power supplies. But we're still a little uncomfortable with the idea of completely eliminating generators. But we were able to reduce our generator footprint by 70%, which translates into significant cost savings on capital, but then also negating the need to truck a lot of fuel to the site. The reason for the generators are really just to kind of keep the network equipment warm while we fail the region over in the event that we've lost both substations somehow over to one of our other regions globally. So, again, the idea is efficiency, economy, exploration and evolution, and probably add elasticity, making sure that facilities are future-proof. One of the things that we deployed in Prineville 1 was a static UPS system, because not all our servers were ready for 277. So we have a cluster of equipment that relied on more legacy servers from our OEMs. So we installed a UPS system that delivered 208. Subsequent to that, knowing that eventually our IT refresh would more than likely be prepared at 277, we, instead of deploying a static UPS system in an electrical room, we deployed in-row static UPS in the locations where typical RPP would be located, with the idea there that when we do our next IT refresh, we're able to remove those in-row UPSs that are providing our 208 solution in Forest City, and instead implement our 277 solution going forward. All right, that's some of the achievements on Prineville. That PUE is 107, that was last year's, is actually 108 today. Our water utilization efficiency, we've been recognized by Engineering News Record, most green building, and we have received a USGBC gold rating on our facility. All right, thank you very much. And if anyone has any questions. And one last note, we publish our accomplishments and our developments on the Open Compute forum, and you're more than welcome to peruse that and participate in the discussion. All right, any questions?
Marco, thanks for that. One question I had is, a lot of what you've been able to achieve comes down to the fact that you guys control the application. Now you're even controlling, you've redesigned the power intake to the servers. With the Open Compute project, does it rely on servers being able to take that higher voltage directly?
The Open Compute?
With Open Compute, if other people like...
Yeah, the Open Compute, we've published the power supplies and working with various server manufacturers to utilize that 277 volt architecture with the 12 volt input, utilizing a higher efficiency, that was part of that, pushing the manufacturers and the entire industry into these ideas of being able to deploy a higher energy efficient solution, avoiding the necessity to do a power conversion at the 208.
My question related to the power supplies as well. The 277 obviously is an enormous improvement in efficiency with a US style voltage. Here in Australia, we're gradually moving to the European standard, the 400 volt, the 230 volt. What have you done in your European deployments in terms of conversions and so forth? Have you stuck with the 277 or have you just gone with the 230?
The power supply can accept a 240 volt distribution, so we haven't had to change anything on the server side.